Okay, so we started talking about systems and Newton's second law yesterday at the end of class, and we were looking at this two blocks connected by ropes question. Okay, and we kind of rushed it at the end of the thing. Okay, so what I want to do is kind of revisit it because I only showed you one of the two ways to solve that question. There are actually two. Okay, so let's kind of look at what we did before. The first thing we did was actually on this original example question, we had to calculate the acceleration of the blocks. Okay? And the purpose of that example was to illustrate that a system all accelerates at the same rate. It may be made up of different parts, but all of those parts will have the same acceleration. The individual forces within the system are going to be different, and that's okay. But in the end, because they're all connected, they move as one single unit. Okay? So we were able to simplify this system, as we can with all systems, to a single mass of 30 kilograms. Okay? 30 kilograms being pulled this way by the force of the hand pulling on the rope of 55 newtons and resisted by a total frictional force of 44.1 newtons. Okay, everyone recall that from yesterday? Okay, so we were quickly able to calculate the net force by simply doing the vector sum of all forces. Okay, and we found that F net was 55 minus 44.1, which was 10.9 newtons forward. Okay, once we knew the net force, then we were able to calculate the acceleration of the blocks, or a question might also say of the system, okay, by simply going by using m times a, but manipulating it obviously for a. So F net over m was 10.9 divided by 30, which came out to 0.36 meters per second squared forward. Okay, now that was how that question kind of started. Here's how someone who's, let's say a jerk like me, okay, might ask this question instead to try and trick you. I give you that same exact example, but instead of saying calculate the acceleration of the blocks, of block 1. Does changing the question to say calculate the acceleration of block 1 change at all the method we just used?
Wouldn't it be, you said 30 kilograms, now just be 10 kilograms?
That's the trick, is it's not. Remember, that 55 newtons is acting on both blocks. It's directly acting on the 10 kilogram block, which is the trick in wording the question that way. Okay? But I don't have enough information to calculate the acceleration of the 10 kilogram block by itself, but I know that the whole system has to go together, and I have enough information to calculate the acceleration of the system. So what often happens is if I word it as acceleration of block 1, people do exactly that, and they divide by 10 instead of by 30, okay? Because they forget that I have to do the acceleration of the system first. Okay? Now, in some situations, a question like that might get set up, and it might only give you enough information to calculate the acceleration of the 10 kilogram block. But in that case, you'd know that's also the acceleration of the 20 kilogram block, but both blocks, of the whole system as a whole. Okay? And that's the thing we have to remember about systems. Okay? Most important thing is that all the parts of the system have the same acceleration because they're connected. If they didn't, they would pass each other or separate. And things that are generally bad in the real world. Okay? Everyone all right with that? Anyone ever seen a truck get jackknifed on the highway when it gets icy? Okay? You know why that is? It's a little bit of Newton's first law, and it's a little bit of Newton's second law. Newton's first law says an object at rest remains at rest, an object in motion remains in motion. The trailer tries to remain in motion. What's the truck doing? Slowing down. So they have different accelerations, which is why the trailer tries to pass the truck. That's what causes a jackknife. Okay? Is the two parts of the system, in fact, have different accelerations. They essentially become separated, even though they're attached. Okay? The trailer pivots around on the pin, okay, and comes around and tries to pass the truck. Okay? And it ends badly. Every single time. Okay? Does that sort of make sense? So in a good situation like this one, which is a bit simplified, this is what we want to have happen. All right, so the second part of this that we looked at yesterday was, all right, we have all of that. We know the acceleration is 0.36. Now it says the force of friction on the 10 kilogram block is 14.7 newtons. Calculate the tension in the rope connecting the two blocks. Okay, so what we did is we went, okay, which block should I use to calculate this? And we decided yesterday we had more information about the 10 kilogram block after being given that number, the 14.7 newtons. So what we did is we drew a free body diagram of just the 10 kilogram block. Because the rope is pulling on the 10 kilogram block, the rope that's connecting the two. Okay? It's pulling which way on the 10 kilogram block? Backwards. Okay? Like, so this is the rope. We're trying to find the tension in this rope right here. Okay? That tension from the 10 kilogram block's point of view is backwards because it's how it's connected to the 20 kilogram block and it's dragging it along behind it. Okay? So that force is resisting the 10 kilogram block. The other forces we know are the ones they told us. The force of friction, which was 14.7 newtons, okay, that was this number here that they gave us, and the applied force of 55 newtons going forwards. Okay, this ringing a bell from yesterday? All right, so now, okay, I'm trying to find this force here. I can't use yet this. I can't use the vector sum of all forces yet. I want to. It's the only way I'll be able to get the tension force, but I can't use it yet. Okay, so what do I have to find before I can do that? I know this number. I know this number. I'm looking for that number, and I don't know this number. But can I find it? How?
Acceleration.
Mass times acceleration. Okay? That's why we did all that work to get the acceleration of the system. It's also the acceleration of the 10 kilogram block. Okay? So now I can say, all right, F net for the 10 kilogram block, okay, is going to be different than the F net for the 20 kilogram block. Their accelerations are the same, okay, but their net forces are a little bit different. Okay, so we got m times a. Okay, F net is m times a, so we're going to take our 10, we're going to multiply it by 0.36, and now we know that the net force is 3.6 newtons forward. Okay, everybody all right with what I've done there? Okay, have I done anything different than any other Newton's second law question? No. I mean, I've broken up a system into two parts, but other than that, everything else is the same. Okay, so now I know this number, I know this number, and I know this number. So now I can find that missing force. Okay, so I would simply go, the force of tension is going to be the net force, 3.6, minus the applied force, 55, minus the force of friction, which is backwards, so I have to make it negative. Okay, that'll give me my force of tension between the blocks. Okay, so 3.6 minus 55 minus negative 14.7, 37 newtons. Okay, so the rope connecting the blocks is pulling back on the 10 kilogram block with a force of 37 newtons. Okay, that was the way we went over yesterday. I could also solve this problem using the 20 kilogram block. Okay, but I have to do one more operation first. Okay, that operation is this. In the original question, they told me the total friction on the entire system was 44.1. Then they told me 14.7 of that was on the first block. Can I figure out how much is on the second block? I just have to do what? Subtract. I just have to subtract those two numbers. Okay, so Okay, so 29.4 newtons worth of that total 44 are acting on the second block. Okay, so now I can do this with the second block. And I can say the second block has how many forces acting on it? Two. Okay, it's got the force of friction, the 29.4 we just calculated, and the tension in the rope, okay, which we already calculated using the first block, but we're going to pretend we haven't done that yet. Okay. Can I calculate the net force on the 20 kilogram block? Yes, because I know the acceleration of the 20 kilogram block. It's the same as the one I calculated before. All right, so F net will be 20 times 0.36, okay, which is going to give me 7.2 newtons. Okay, so the net force on the 20 kilogram block is 7.2 newtons, which makes good sense. It's twice the amount of net force on the 10 kilogram block, which had half the mass. Okay, that way they get the acceleration to be the same. Okay. All right, so now I know that net force. Now I can say net force is the vector sum of the two forces acting on the 20 kilogram block. Okay, and then I would say force of tension is 7.2, okay, minus negative 29.4. I'm looking at that and thinking that's probably going to come out to 37. Would you agree?
So the force of friction is the same, or the force of tension is the same for both?
Right.
Yeah.
That's how tension works, is because it's a rope, and it's going to pull differently on the two, it's going to pull the two ends in different directions.
And would it be the same if you were still pulling backwards, but the 10 kilogram block and the 20 kilogram block were just switched places? Like you were pulling the 20 gram block first, and then the 10 kilogram block was behind that.
Yes.
It'd be the same.
It would be the same, yeah. Because we'd still have a total of 55 and a total of 44.1, so even if I reversed it, it wouldn't make any difference, yeah. Okay, all right, so we got our tensional force there, okay, so we got 7.2, okay, minus negative, our answer from the previous thing here. Okay, yeah. We got 36.6, but still 37, okay, and that's just because of a rounding issue, okay, nothing else. All right, everybody okay with that? So, system questions get a little bit tricky, okay? But as long as we remember that whole thing about the accelerations are the same, we're okay. So, here's what I would like you guys to try. Talked about this question yesterday. The 2 buckets of nails question. Okay, so you have 2 buckets of nails hung one above the other that are pulled up to a roof by a rope. Each bucket has a mass of 5 kilograms. The tension in the rope connecting the buckets is 60 newtons. Calculate the acceleration of the buckets, plural. Give you a few minutes on that one. Okay, so in a question like this that's got 2 masses in it, there's 3 possibilities. They may not all be possible, but they're possibilities of ways to solve this. I'm trying to find the acceleration of the buckets. That means the whole system. What I need to remember is that that acceleration is the same as the individual parts. So the 3 choices for how to solve this are solve it as a system, solve it for the first mass, or solve it for the second mass, because you'll get the same answer regardless of which way you solve it. The only problem is 2 of those ways are not possible in this question. Okay? There's only one of those 3 options that can actually work. So here's my situation. I have 2 identical buckets full of nails. Okay? And they each have a mass of 5 kilograms. Okay? It tells me that they're being pulled up by a rope. Okay, so that means that there's an upward force here. Do I know what it is?
No.
Do I have any way to get it?
Not yet.
Not yet. And basically not, well, by the time I got the acceleration, it'd be pointless to do it. I'd be able to do it then, but why? I've already got the answer. Okay, so if I don't know that force, I mean, I can calculate the force of gravity acting down on this 5 kilogram mass, right? I can calculate the force of gravity acting down on this 5 kilogram mass. I could do this if I wanted to, and say 10 kilograms, and have the force of gravity. Okay, it would be 98.1 newtons. But I still run into the same problem. I don't know what this force, which is the one directly attached to the top bucket, is. But here's what I do know. I know this rope has 60 newtons worth of tension in it. From the bottom bucket's point of view, that force is which way? Up. Do I know how much downward force is acting on the bottom bucket? But I can figure it out, right? It's gravity, so I can figure it out. So I don't have enough information to do this question as a system. I don't have enough information to solve this using the top bucket, but I can use it solving the bottom bucket, because it's the only one I have two forces for. This is, in the end, still an elevator. Okay? It's a system elevator, it's two cars, but it's still an elevator. Okay? So I'm simplifying it down to just the bottom bucket.
Yeah.
Okay? So I'm going to calculate the force of gravity acting on the bottom bucket by going m times g. So 5 times 9.81 is going to be 49.05 newtons. Okay, can I calculate the net force acting on that bucket? Okay, so I'm going to go F net is the vector sum of all forces, so that'll be the force of tension plus the force of gravity, 60 plus negative 49.05, which is going to give me 10.95 newtons up. Okay, can I calculate the acceleration of that bucket? Is that the acceleration of the buckets?
Yeah.
Absolutely.
Wait, why is it the acceleration of both buckets if we eliminated the one on the top again?
Because they have to go up at the same rate,
Oh, okay.
right? If the bottom one were to accelerate faster than the top one, it would pass the top one. I've never seen anyone do that. In all my years of lifting things and watching other people lift things, which sounds really boring, but you know, it's just because I'm old. Okay, I've seen that. I've never seen the thing on the bottom pass the thing on the top.
So would it also be 60 newtons for the one above that bucket?
No, that's the thing. The one above that bucket would have to be twice that,
Oh,
because it's lifting twice as much mass. But
Right.
we don't know that yet.
right.
And we can't just go, well, I'm going to assume this is what it is.
Right.
Right? So, what I'm going to say is, because this is the stuff I'm sure of, I'm going to use the bottom bucket and then apply the acceleration of the bottom bucket to the whole system, because I know I can do that. Okay? So when I go, acceleration is F net over m, okay? I got 10.95 over 5, which is 2.2 meters per second squared, up. That's the bottom bucket, the top bucket, both buckets. All right? So again, you're probably going to get sick of hearing this, but was there any tricky math in there? No. I subtracted some numbers and I divided some numbers and I multiplied two numbers. That was it. Okay? But it's tricky to see what's happening and go, all right, I can do this. I know that this is true. So if I can get this thing, I can apply it to that. That's the tricky part. Okay? Is seeing the physics and getting through that. Okay? Like, I have no doubt of your math ability to do this. None at all. Okay? I'm supremely confident in that. It's getting to the math that's challenging. And I can't tell you how many students I've had in my years of teaching who were brilliant at math, like mathematician brilliant at math, and struggled in physics. Okay? There's like, just want to do the math. Well, then go do math. Physics isn't about the math. Physics helps you, like math helps you get an answer in physics, but it's not about the math, it's about physics. And that's the tricky part. Okay? It's why someone like me, who's not very good at math, who, like last night, both me and my son were like working on his math 10, and I was the only one crying. Okay? You know? Yeah, I'm like, look, how do I factor a trinomial? I don't know. Do you know how long it's been since I factored a trinomial? I figured it out because I'm good enough at math to subtract numbers and figure out how long it was. It was way too long. But yeah, you don't have to be really good at, I mean, it doesn't hurt to be good at math, make no mistake, but you don't have to be good at math to be good at physics. Okay? All right. Oh, no. You look so hard. Okay. Is this also a system?
Yeah.
Okay. So in this system, I got two masses hung over a vertical pulley. Okay? So one of them's 35 kilograms, the other one's 25 kilograms. So let's say I'm holding this pulley system and I let it go. What's going to happen?
That's right, yeah.
Yeah, that's pretty straightforward, right? I mean, the 35 kilogram mass is heavier, so it's going to go down and it's going to lift the 25 kilogram mass over the pulley. Okay, it'll stop when the 25 kilogram mass crashes into the pulley. Okay, but during that time, there's going to be an acceleration. Now, here's where people are like, Coder, you said the accelerations are always the same. I did, and it's true. They don't have to be in the same direction. They're going to have the same magnitude, but slightly different direction, because in this thing, the pulley is a lever, right? And so it is going to change the direction the force is acting from the perspective of the different masses. Okay? They still have to accelerate at the same rate. Otherwise, it would be possible for one to pass the other, okay? Which is still not something that happens. So we want to determine the motion of each object once the objects are released. So basically, they want the acceleration of the system. Okay? I can apply the directions after. I know the magnitude of their accelerations is going to be the same. Okay. What are the forces in this system, assuming that this is a light, frictionless pulley? And by light, they mean it also has no mass, so the acceleration of the pulley is moot. Okay? All we have here is two masses. What are the two forces?
It would be gravity for both.
Right, it's gravity for both. Those are the two forces. Okay? Gravity is working against itself in this question. Okay? In fact, if this were 35 and 35, what would happen? It would stay, because the net force would be zero, but it's not. That would be too easy. Okay, so we've got the force of gravity here. Okay, and that'll be m times g, so 35 times 9.81. Okay, so 343.35 newtons, and force of gravity here. Okay, also m times g. Okay, 245.25.
Oh, so you found the force of gravity for both?
For both, yeah. Because those forces are going to oppose each other in this question. Okay, and that's the important thing for us to realize. Even though it's gravity, it's opposing itself. Okay, because it's acting on two different parts of the system differently. All right, at this point, can I simplify this system? How would I simplify? What would it look like?
Add the weights together and then just have 245 newtons up and then 343 newtons down.
Yep. Okay, I usually draw them horizontally, but we could draw them vertically too. Yeah. Okay, so we combine those two masses, 35 plus 25 is 60 kilograms. Okay, that's 60 kilograms worth of mass that's being moved by the net force acting on this system. All right, so I'm going to have the force of gravity here, 343.35, okay, and the force of gravity here, 245.35. Oh, sorry, 0.25. Okay, can I calculate the net force on the system here? Absolutely. Okay, so F net is going to be 343.35 plus negative 245.25, which is going to be 98.1 newtons. I calculate the acceleration of the masses? All right. So if I want to calculate the acceleration of the 25 kilogram mass, what do I divide by? 60. And again, is that how a jerk like me would ask that question? Absolutely. I would not ask it like this. Determine the motion of each object. I'd say determine the acceleration of the 25 kilogram block just to see how many of you I could get to put 25 in there. Okay? Because what's the thing we're supposed to remember about a system? All the parts accelerate at the same rate. Combine the mass. Okay? So 60. Okay, so 98.1 divided by 60. Right, 1.6, we only have 2 sig digs, so 1.6 meters per second squared. Now, the way the question was worded, I have to leave the answer like that. Why?
Because one of them will have an acceleration down, one of them will have acceleration up.
Yep. If it said calculate the acceleration of the system, I have to leave it like that. That's the magnitude of the system's acceleration. I cannot give a direction because different parts of the system are going different directions. Okay? This question said determine the motion of each one of the objects. So now I could say, okay, the 25 kilogram block will accelerate at 1.6 meters per second squared up. The 35 kilogram mass will accelerate at 1.6 meters per second squared down.
Could you put it as positive, negative?
Well, given the context of the situation, up and down is kind of clear, but I would say I probably wouldn't mark it wrong if you put positive or negative. In that case, I would define that in your diagram. Like, I would say, like, something like that. Okay? Questions on that one? Okay. Does it sort of make sense though? Is it a lot like the 2 blocks in the other one? Okay. They're very similar, right? So that's what we have to know kind of about systems. A pulley is also a system. Okay? It's why, even with a pulley, you can't lift something heavier than yourself with a single pulley. Okay? Because if the thing is heavier than you, all you can do is hang on the rope. Force of gravity on the other side is greater than your force of gravity, so you don't go anywhere. You just hang there on the rope and look foolish. Okay? But if you had more than one pulley, could you do it then? Yes, because if you have a multiple pulley system, it becomes a force multiplier. We don't go into that in Physics 20, so okay, we don't have to worry about that, right? But for a single pulley system, okay, they pull directly against each other. Okay, try this one. So there are 3 masses in this system, okay? 2 buckets or pails and 1 big tire on a frictionless table with light frictionless pulleys. Okay? We always have to put that in there, right? Because if the pulley had mass, would I have to combine the pulley's mass to the system? Yeah, because it would also be accelerating. Okay? We simplify. We don't worry about the mass of the pulley. Okay, so first thing is we want to identify the forces that are acting. How many forces are acting here? 2. Yeah, the force of gravity on the 2 pails. The table is frictionless, so there's no forces other than, like, gravity and normal force was cancel anyway, acting on the tire. Okay, so the only forces we have are the force of gravity here, and pail C is 6 kilograms. Okay, so that's 58.86, right? Okay, 58.86 newtons there. Okay, that's the force of gravity there. And then this one here is 8 kilograms. Okay, so the force of gravity on that one, 78 point something. 8 times 21, 78.4. Right. Okay, those are the only forces acting in the system, is those 2 forces. Can I calculate the net force acting on the system? Yep, I just have to subtract these 2 numbers. Right, so my net force okay, will be 78.48 minus 58.86, which should give me 19.62 newtons. Okay, everybody all right with that? Don't be impressed, I wasn't doing that in my head, that's like memorization. They're 2 kilograms different, which means they're 20 newtons different, 19.62 newtons.
I was gonna ask, so are the ropes attached to like the sides
Of the tire? Yeah, they're tied on the tire.
So they're not attached to each other?
No, they're not. If they were attached to each other, the tire would still have to slide,
Okay.
right? Unless it could slide over the tire, which would bring friction in and all of that. So no, they're tied to the tire.
To the
It's
sides?
2 separate ropes, yeah, it's 2 separate ropes,
Okay.
and they're attached to each side of the tire.
Okay.
Okay, so now that I've got the net force, they want the acceleration, and look at the wording of this. Calculate the magnitude of the acceleration of the system, because we can do nothing else. The system has 3 different parts. All 3 parts go in different directions. So all we can do is say the system accelerates at this rate. But we cannot give direction with that wording. Okay? So acceleration is going to be F net divided by m. So that'll be 19.62 divided by, what's our total mass here? 8 and 6 is 14 and 20 is 34. Okay, so 19.62 divided by 34, and we are looking at an acceleration of 0.58 meters per second squared. And that's it. I can't put a vector on it. Okay, tomorrow we're going to start looking at some other vector-related types of Newton's second law questions. Okay, so we might have to do some, tail to head, find an x and y kind of stuff tomorrow. Okay, guys, remember, if this is giving you trouble, you're struggling with it, whatever, come in and see me for help. I'm here all the time because I have no life. Okay?